The topic that we'll be discussing today is specific heat capacity. Before getting into the concept of specific heat capacity, we'll first go over the content of this slideshow. Other than the basic concept of specific heat capacity or the formula that we'll be using, the next thing that we'll be discussing would be the heat equation and some of the questions followed by it. Then the difference between thermal capacity and specific thermal or heat capacity, and what does the word specific in this terminology really specifies or tells. After that, we'll be talking about the applications of different materials that have high specific heat capacity or low specific heat capacity. Example of a material or a substance that has high specific heat capacity is water, and there are a lot of applications of water that are really dependent on this property of water as a high specific heat medium. So, what is specific heat capacity? In order to understand the main concept, let's just imagine the scenario that there are two pots with same mass of different materials. This pot over here contains water and it has 1 kg water. It's really important to note that we're talking about the quantities in terms of mass and not in volume or area. So the thing that we're keeping in constant here is masses. So both of them are 1 kilograms. 1 kilogram of water, and this one right here contains 1 kilogram of paraffin. So if you heat up 1 kilogram of water and 1 kilogram of paraffin, they're heated in turn for the same amount of time by the same heater. So what we're doing is that we're taking the same time, so time is constant. And what else is constant? Time is constant, and by the same heater. By the same heater, it basically refers to the heat transfer or the um, energy transferred to these systems. So the number of kilojoules or the number of, let's just talk, say we talk about joules. So the time in seconds is same, the number of joules transferred or the heat transferred is same, the mass is same. What is really the quantity that is being judged over here? So we really expect these two quantities to have their temperatures raised by the same amount. However, that is not the case. That is not how it works. Uh, what happens is that the temperature rise of the paraffin is about twice that of water. Now, the reason why there is a difference in temperature rise or the heat, uh, really the heat energy that was then translated in form of temperature rise, although same amount of heat was gained by both of these materials, is because of their different specific heat capacity. So since the heater gives equal amount of heat energy to each liquid, it seems that different substances require different amount of heat to cause same temperature rise. In the mass, let's just say 1 degree Celsius and 1 kg mass. So if you're talking about, the other terms like that we keep the temperature rise same and we're talking about the amount of heat transfer, then we can also say that it really tells us how subs different materials or different substances, they require different amount of heat for them to have the same temperature rise. Let it be 1 degree Celsius increase in temperature for the same mass 1 kg. The thirst of a substance for heat is measured by its specific heat capacity. So the amount of heat that it requires in order to exhibit 1 degree change in 1 kilogram of mass is called the specific heat capacity. The specific heat capacity of a substance is the heat required to produce 1 degree rise in 1 kilogram. So this is this right here is basically the this right here is basically the definition of this. This is the definition that is required in the exam questions. So it's really important to mention two things in this. First one is that we're talking about same temperature rise, which over here is referred as a threshold temperature rise given as 1 degrees. You can also write same temperature rise, and the other thing is 1 kilogram. We're going to discuss how this 1 kilogram is really important in the definition. So heat, like other forms of energy, is measured in joules, and the unit of specific heat capacity is then joules per kilograms per Celsius. Because we're basically measuring that how many joules are required for 1 kilogram of an object or substance to get a temperature rise of 1 degree. So joule per kilogram per Celsius. If we're talking about different temperature rise scales, then obviously this changes, but in SI units, these are the units that we'll be talking about. In physics, the word specific basically means unit mass. So this 1 kg or this kilogram over here is basically brought in by the word specific. But it basically means that we're not talking about a whole system or a whole material, or we're not taking into account of the mass that that object has. We're just talking about a property. So when we're talking about the word specific in physics, it means that unit mass of an object or unit mass of a material. This is the same diagram. It basically shows how this specific heat capacity concept is applied in different applications in our daily life. That the reason why we have these Teflon aligned or these plastic frying pans or these iron frying pans, and then we have these earth pots over here, because there are different reasons for them. The reason why we cook our food in iron frying pans and then we put them in earth pots or the ceramic ones is because iron frying pans, they're easy to warm up, so their specific heat is smaller. If specific heat is smaller, basically means that they require less heat to get more temperature rise. And we have pots or ceramics or earth pots uh, in which we keep our food to keep it warm. It has higher specific heat, so that basically means that it requires higher heat energy to get temperature rise of uh, some specific amount. However, as we're talking about increase in temperature by providing some material with heat, we can also talk about the vice versa situation, that if an object needs more heat to gain 1 degree temperature rise, obviously uh, it will take more time, or it will give more heat away to basically get that 1 degree temperature decrease. Heat equation. Now we're talking about the heat equation. If a substance has a specific heat capacity of 1,000 joules per kilogram per degree Celsius, then 1,000 joules raises the temperature of 1 kg by 1 degree Celsius. And if you multiply that by 2, that if you have 2 into 1,000 joules, then it raises the temperature by 2, or temperature of 2 kilogram of an object by 1 degrees. So basically what we're doing is that if you want 3 degree rise, then you will require that specific amount of heat multiplied by 3. So that really tells us how these relations are working. that if we increase the amount of substance or we increase the amount of temperature rise, then we will have to increase the amount of heat given to some object. So that really tells us that we're basically dealing with direct proportionality, and all of these terms are, directly proportional to the heat energy that will be required. So that is 66,000 joules will raise temperature by 2 kg of this substance by 3 degrees. So we basically multiply 2, multiply by 3, multiplied by the 1000 specific heat capacity that we have. We've obtained this answer by multiplying together the mass in kilograms, the temperature rise in uh, degrees, and the specific heat capacity in joules per kilogram Celsius. So this is the formula for specific heat capacity, that mass is equal to specific heat capacity multiplied by the temperature change. Q is equal to mass multiplied by the specific heat capacity multiplied by the temperature change. So where Q is the heat required, C is the specific heat capacity. So specific heat capacity is basically um, a property, a measurement of a property. So it is already given, and we cannot really. And each substance or each material has its own one definite value of its specific heat capacity. And these are some examples that if the temperature of a substance fell by 3 degrees, then the heat given out would also be 6,000 joules. And that if we require a large amount of heat for an object to heat up, then obviously the amount that will be given out when that object cools down, that will also be the same or would be a large amount. So in general, we can write the heat equation as heat received or given out is equal to mass multiplied by the temperature change multiplied by the specific heat capacity. So if this is an example, let's just call it example 1. If the temperature of 5 kilograms mass of material specific heat capacity 400, so this is the value of C right here, and 5 kilograms is the mass M, and what is the delta, sorry, theta, delta, whatever you call it. We're basically talking about the temperature change or the temperature rise. So temperature rise is 25 minus 15, that is 10. So what we're going to do is if we multiply 5 multiplied by 400, then multiply by 10, we're going to get the heat received, that is Q. So 20,000 joules is basically what we require in order to get um, the heat transfer, in order to get that body or that 5 kg mass to let temperature rise from 15 degrees to 25 degrees. Now we've talked about heat capacity, or sorry, specific heat capacity, but why is thermal capacity a different thing than specific heat capacity or specific thermal capacity? So the thermal capacity of a body is the quantity of heat needed to raise the temperature of the whole body by 1 degree. In this one, we're not taking in account of the mass. We're just talking about um, how much heat will be required for the whole body that is under consideration uh, to get a temperature rise or a temperature change of 1 degree. So for a temperature rise of 1 degree, the heat equation becomes heat received is equal to mass multiplied by 1 multiplied by the specific heat capacity or the thermal capacity. So that really turns into MC delta T. The reason is that in this case, we have really specified that when we're talking about the thermal capacity of an object, we're just talking about uh, 1 degree temperature raise. So it's heat equation, but MC delta is equal to Q. So in this case, the difference is that this delta is equal to 1 because the temperature rise is 1. Thermal capacity is measured in joules per degrees, that is joules per degrees or joules per Kelvin. For a copper block of mass 0.1 kg and the specific heat 390, thermal capacity would be equal to 39 joules per degree Celsius. Now, different materials or different substances have different specific heat capacity. Let's just say if we talk about water, it has high specific heat capacity. So water has high specific heat capacity, which basically means that it requires a lot of heat to get its temperature raised by some amount. So as a result, the temperature of the sea rises and falls more slowly than that of land. This is one of the examples that if in a setting, let's just say, yeah, in this setting, water's high specific heat capacity helps to moderate daily air temperature around large bodies of water. So if you're standing on a seashore, you can really observe how both of them are exposed to same environment, but water is usually cooler than the warm sand or the land that you were standing on. That's really because of the high specific heat capacity of water that it needs more heat to get that same level of temperature rise than the land. So a certain mass of water needs 5 times more heat than the same mass of soil for its temperature to rise by 1 degree. Water also has to give out more heat to fall. So this is obviously, a relation that goes both ways. That if it needs more heat to get a temperature raise of 1 degree, then it definitely needs it gives out the same amount of heat when the temperature falls. So at night time, it's the opposite. That the water is warmer and the land it is cooler because of the high specific heat of water. Since islands are surrounded by water, they experience much smaller changes of temperature from summer to winter than large land masses such as Central Asia. So that's a really good example to understand how uh, the high specific heat of water can really impact on such huge temperature or weather changes. The high specific heat capacity of water, as well as its cheapness and availability, accounts for its use as cooling engines and in radiators or central heating systems. So it's really a good coolant too because it has a threshold value of heat that it requires in order to get to that level of temperature rise that that is in the limits of safety or other specific limits that are given for the usage of that device. The specific capacity of water, and yeah, that's basically the same application of the land and sea. Okay, now we're talking about low specific heat capacity. Now, if you basically imagine an object with low specific heat capacity, you are thinking of something that really requires uh, less amount of heat but gets really heated up easily. So if you if you think deeply, then that's basically the definition of conductors. So most conductors basically are they have low specific heat, obviously. So it's not a given, but in most cases, objects with low specific heat they are better conductors or they're good conductors. So that basically brings all the metals in this category. So all the metals are do have low specific heat capacity, relatively speaking, obviously. So a substance with low specific heat capacity, specific heat requires relatively little heat to raise its temperature. Copper has low specific heat. Metal atoms in pure metal are very close together and are able to transfer heat easily via conduction. So this also tells how liquids have higher specific heat capacity than solids because the molecules of liquids they are further apart and hence the transfer of energy or the vibration that takes place slower or takes longer time than how it happens in metals or other solids. So the amount of energy it takes to heat a metal is relatively smaller to that of water, for example. This is it. Thank you.